what charge is this molecule before any titration happens. And here is the molecule. So what is the charge of this before any titration occurs? Oh, sorry, I might not have started yeah, I did. So you guys can go ahead and answer that. It should have been started, yeah. Okay, so sorry again, here's the molecule. So the initial charge. Okay, one more second. Okay. Okay. We need to talk about this. Okay. So the answer is 2. Okay. So let's look at this molecule. So we start out with this, right? And if we take a close look, the spots where we have pKa's, they're not fully protonated, right? This nitrogen can handle one more hydrogen bonds. Both of these nitrogens here can handle an additional hydrogen bond. So what you're going to see is you're going to want to protonate these, right? Because you want to get it to have all 4 bonds, and that will give it a positive charge, right? And so the total charge will be +2. Okay, so again, you want to make sure the molecule is fully protonated, okay? Over here, we can't protonate that, right? We can't protonate that anymore. Otherwise, it'll turn into water and then it'll leave the molecule. So these can be protonated once more because they're not fulfilling all 4 of their bonds since they have an extra lone pair available here. So yeah, hopefully that makes sense. For this question, would both NH2 plus and NH3 plus depronate at the same time? Close to the same time, but no, because they have different pKa's, right? So this one would deprotonate first, and then this one, if that makes sense, Jacob. Hopefully. But close, though. They are close in pKa's. Yeah, they do seem pretty close, but not all the way. Okay. So let me know if there's any questions on that one, and I will go to the next question. Okay, so this question is just asking, how do you calculate the pH at the beginning of a titration at the initial point when you have a weak acid? I have another question about the charges. To figure out charge, we need to check to see if each group can take another bonds. The only one you really are concerned about is that nitrogen, though. That's the one you're going to see the most. So yeah, if the nitrogen is fully protonated, then that's how you want it to start out. If it has like a lone pair and it's not, finished bonding, again, out of a total of 4 bonds, it can be protonated once more. Okay, but yes, so this question is, how do we calculate the pH at the beginning before we add base? Okay, I'll give you guys another second. Okay, I'm gonna go ahead. Perfect, good. So this was not supposed to be like a trick question. It just wanted to make you remember, like, we don't have any base, and so this is simply going to be a weak acid calculation at the beginning. Okay, great. I don't think I had anything on here for that. Maybe I did for number 4, right? Okay. So basically here, I set up an example so we can try to calculate it. And so all we need to do is fine. The first, because we don't have the Ka values for this, but the first step would just be to find the molarity, like normal, and then do a regular weak acid calculation using the Ka, which we don't have, to find the H plus concentration. Okay, and then with that you can find the pH. Okay, so that seemed good. Okay, this next question is asking, how do we find the pH at the third equivalence point if there's 4 equivalent points in total? So Jacob, yeah, we have, yeah, these questions are separate. Yeah, so don't worry about number 3's charge question with the questions, these conceptual questions about pH. Yeah, don't worry, don't confuse them. For looking at initial pH, or sorry, initial charge, does nitrogen want to have 0 lone pairs and oxygen, we want to have 2 lone pairs still? Yeah, basically, you can think of it that way. Yeah, so you want nitrogen to have a positive charge and at the beginning, okay, and oxygen will not have any charges at the beginning. Okay, so yeah, we're looking at the third equivalence points. Okay, let's see what you guys said. Perfect. Oh my God, good. Okay. We are not going to be looking at the averages of the equivalence points, only the average of the pKa's. And so if we take a look here, I kind of set that situation up. We don't know what that question mark is. And so what we're going to do is we're going to take the average, let's say, of 9.04 plus 12.48 divided by 2, and that will give us our equivalence point pH there, the third equivalence point. So the answer to that would be 9.04 plus 10.76. That would be the pH right there at that question mark. Okay, good. And my next question is, how do you calculate the pH at the second halfway point? I'll give you guys another second. Okay. Okay, wow. Interesting. Yeah, there actually are pH equals pK at the second halfway point. Yes. However, what if you don't know what the pK, I should have mentioned that. What if you don't know what the Ka values are? And I'll go through this. Okay, so depending on what information you're given, you can find it different ways. But what if you don't know the Ka values? And I should have put that in the question. So sorry about that. So let's take a look if we don't know what the Ka values are. Okay, so this is all the information we know. What's in front of us is all we know. How do we calculate that question mark there? Can we use the average of these two numbers? Can we do that? We just find the average of those. Can we do that? You guys let me know. Right. We cannot. The only way to do this is by using the same formula we just did before, which is pKa in this case, let's say 2 plus pKa 3. We're looking for pKa 3. Divided by 2 is equal to the second equivalence point pH. So if we do that on, let's do it on the right side here. So we don't know what pKa3 is, but we do know what pKa2 is. So we'll do 6.1 plus pKa3, which we don't know, divided by 2, and this is equal to 7.57. Okay, so if we were to solve for this, we would just solve for pKa3. And we would get 9.04. Okay, any questions on this? Okay. Sorry. Okay. Yes, if there was a K, if you did have the Ka values, you can take the negative log. Yes. To find the previous question. Okay, so this question is asking, how do you find the pH at the very end point? Okay, so theoretically, well, I won't say anything. What do you guys think? So you start out with a weak acid in this case. Okay, one more second. Okay. Okay. Yeah, so it's going to be a weak base calculation, right? Because theoretically at the very end, we shouldn't have any weak acid left. We shouldn't have a strong base left. We shouldn't have anything but the conjugate of what we started with, which was a weak acid. And we're going to get the conjugate base. That's the only thing that should be left at the very end. Okay, so let's take a look here. So if we were to do this problem, if we were looking at the endpoints, so the first thing you would do, you have the number of moles. And so in this case, yeah, you have the number of moles. And then to find the pH, what you would need to do is set up the weak base calculation like normal. So you would do Kb, which you're not given here, is equal to the initial, well, you'll have x squared over the initial molarity, which is, you'll have to, so, okay, so we can do an example. We're going to go through many examples today, though, especially with the practice quiz. So just moles of acid divided by total volume after adding 3 equivalents of base would work. To find the total, to find the endpoint molarity of your conjugate base, yes, exactly. So you would do 2.2 moles divided by the total volume to find the concentration of conjugate base at the end. And then with that, you'll put it over here. Okay, so hopefully that makes sense. Okay, so let's look at the next question. Sorry about that. How many moles of NaOH needed to reach the endpoint when starting with 0.3 moles of tripartic acid? Jacob asks, and you're using the final Ka to find the Kb, right? Yes, always use the final Ka to find the final Kb, right? Yeah, so this is kind of a conceptual question to make sure you're understanding how titrations work. Just asking how many moles of NaOH do you need to complete a titration with a triprotic acid, okay? Okay, one more second. Good. Okay, so I'm glad. I just wanted to make sure you guys got that down. You need 3 times the amount, right? If you wanted to get, we'll actually see the next question. But to visualize what's going on here, just to make sure, this is what you'll have. So if you start out with 0.3 moles of your triprotic acid, you're going to have an additive effect here. You'll need 0.3 moles to reach the first equivalence point with 3.3 moles of NaOH, and then you'll need 3 times that to reach the final endpoint, right? Okay, good. So how many moles of NaOH do you need to titrate 1.5 equivalences of 0.5 molar carbonic acid in 1.5 liters? There's only 2 calculations you need to do for this. Okay. Okay, good. I just want to make sure again. I'm really glad, 100%. Wow, you guys, I'm impressed. Okay, so yeah, I just really wanted to make sure you got these concepts down because if you understand the concept, if you understand what's going on, you'll be able to always get the calculations right, no matter what kind of scenario you're presented with, right? Okay, so you guys basically understand. This is how you would have gotten that number. Okay, good. Okay, so another kind of conceptual question. When is an acid in its ionized form? Okay, what does ionized mean? It just means when it has a negative or positive charge, whenever it's charged, right? So when is an acid in its ionized form in respect to the pKa? One more second. Okay. Okay. Good. So basically, I'm going to kind of like show you guys what that looks like. So when the pH is less than pKa, we're going to have the predominant form, the non-ionized form. So the non-deprotonated form, it's still going to be protonated. Most of it will still be protonated before the pKa, okay? When the pH is equal to the pKa, the concentrations of both the non-ionic and the anionic form will be equal. Okay. And then when the pH is greater than the pKa, then the ionic form, the deprotonated form would be dominant there, okay? And so I'm gonna have a similar question right now, asking about, what about bases, right? What happens with bases? When are they in their ionic form? Okay, okay, good. So what we're gonna see is the kind of the opposites. And I'll also explain how you should think about this entirely. But again, yes, so when the pH is less than the pKa, we're going to have the base, here's imidazole, in its protonated form. And then the non-ionic form will be not dominant here. When the pH is equal to pKa, we're going to see the concentrations of the protonated and not protonated form equal. And then when the pH is greater than the pKa, we're going to see that the deprotonated form, which has no charge, will be dominant. Okay, so how do we put that all together? Okay, so this was so random that I drew Patrick, but anyway, the protonated form will always exist before the pKa, right? So if we see the bases here, the bases are protonated before the pKa, and then they're predominantly not protonated after the pKa. Similarly, over here, with the bases, um, the protonated form is dominant before the pKa, and then the deprotonated form is dominant after the pKa. Thank you, guys. Okay, so again, as a rule, the acids will be ionized, as Patrick is saying here. The acids will be ionized when the pKa is greater than the pH is, sorry, pH, pH is greater than pKa, and bases will be ionized when the pH is less than the pKa, okay? So that's how you put that together. Hopefully, are there any questions on that one? And I think we're going to thermo now, maybe. Yeah. What does it mean before pKa? It just means the pH is less than the pKa. That's what I mean, sorry. Does that make sense, Jerry? Yeah, okay. All right. Okay, so this is thermo now. We're looking at what causes entropy of the system or a reaction to increase. When something's going from a solid to a gas, when something's going from a liquid to a solid, and so on. Right. Perfect. Okay. So let me ask you another question. What causes entropy of the surroundings to increase? Okay. Okay, good. You got the idea. I'm glad, because I remember when I took the class, he didn't really cover. what happens in the surroundings. Exothermic reactions always increase the entropy of the surroundings, correct? Hold on, yeah, because there's actually an equation. Yes, so I believe you're right, Jacob, yes. Because you'll see an equation that looks like delta S of the surroundings will equal negative delta H. So exactly perfect, that's the one. Okay, good. So first, let's define entropy. What do you guys, put out some words, some nouns that describe entropy, or some descriptions in the chat or wherever. Disorder, okay, that's one. Chaos, randomness. Okay, what's one more way of thinking about it? Maybe in kind of terms of like, without saying the word, maybe like availability of positions, maybe. It's another word for like positions. Microstates, yes. So yeah, number of microstates. Good. Okay. So basically, what I kind of wrote down here was how to summarize or how to look at, which you guys got for the most part, entropy increasing in the system, in the reaction, and then what that looks like, how that influences the entropy of the surroundings. Okay, so if you notice, they kind of have an opposite effect, right? If we want to increase the entropy of a system, we want things to become more into these less ordered states, right? But that has a kind of inverse effect on the surroundings. So yes, so these will have an inverse effect. These will if you move a liquid to a solid, that will increase the entropy in the surroundings, right? Okay. Any questions on that before I move on? Yeah, go ahead. Microstates. So microstates just means like position, but temperature will influence a lot, right? Will influence it a lot. Temperature will directly also increase the microstates because, well, no, it won't. No, sorry. Microstates is simply a measure of position, yeah. Temperature will just increase the kinetics. So can you go over why entropy increases going towards a solid for the surroundings? Yes, so the surrounding means everything that's not in the reaction, right? And so in the system, this makes sense, right? Where if we're going from a liquid to a gas is much more disordered than a liquid. Similarly, a solid is much more ordered than a liquid or a gas. So so let's say going from a solid to a gas, that's really a huge increase in entropy, right? However, if we take into account the surroundings, which is not the reaction, right? We're not thinking about our liquid or our gas in the reaction. We're thinking about what's happening in the surroundings, right? And that'll have kind of an opposite effect. And so the way we increase disorder in the surroundings will be through doing the opposite, right? How do we take into account microstates in thermal questions? Like, do you mean like that one question on the discussion worksheet, for example, Fiona? Like the one with like the circles and where they are located, maybe? Can you relate this to delta S of the universe? For a certain reaction, that value is always constant. I believe yes, Jerry. Yes, I think you're right on that one. And Fiona, yes. So if you have, let's say, yeah, like in the discussion worksheet, like let's say this is like your space that you're able to go in. If all of your particles stay over here, is that high entropy or low entropy? Low, very low, yeah, very low. So the number of microstates in these kind of positions is very low. And so, however, if we had particles spread out, this would be high entropy, right? Because there's so many possible microstates that they can be in because they have more space to, to kind of move around in. So that's one way of looking at things. Yeah. I was also thinking of questions like where it asks to calculate entropy. So when you calculate entropy, we'll be looking at this equation here, which we're going to look at right after the next question. And then Jacob asks, for that discussion worksheet question, more spread out would mean more microstates and more entropy, right? Similarly, like in life, in biology, you're gonna, let's say you have like a membrane here. Let's say this is semi-permeable, okay? So that things can flow in and out. What life does, and this is one of the really interesting things that distinguishes life from non-life, is how it goes against the equilibrium, right? How it decreases entropy, right? You might ask, but doesn't all life have to, doesn't the universe have to go to a net decrease or increase in entropy? And yes, so the world is always getting more chaotic, the universe is getting more chaotic. But what life does is it can like couple reactions basically. And so what it can do, and which is special about life and life chemical reactions, is that it can, let's say this is the outside of the cell and this is the inside of the cell. It can, what if it like wants a higher concentration of a certain molecule on the inside of the cell? It can do that, right? So it can do that. And so this is going to be a very low entropy state. And how does it do that? It does that through like protein channels. It really controls what's going in and out. So this is going to be low entropy, right? Because what it wants to do, it wants to diffuse back and forth like there was nothing there, right? It wants to be high entropy again, okay? But life controls that, right? Okay, so that's enough of that. Okay. Okay, so what will delta G be during a phase change? That's okay, Catherine. Okay, I'm gonna go forward. Okay, good. So it will be 0, okay? I wanna ingrain this in your minds, okay? Because delta G is gonna be, it is going to be at equilibrium in that state. So basically, okay, yeah. So we're gonna look at this equation in the next question. That was just a one point question. I just want to make sure you guys understood that. Okay, because then you can apply that. You can apply that question to calculations. So make sure you know this concept. It's very important for you to do calculations. Okay, so delta G. So what is a phase change, right? Phase change could be boiling, right? It could be any time when things are changing their state of matter, right? Okay. So I want you guys to answer this question as well. It's a clarification question. if anyone's here for the quiz walkthrough, we're almost done. So it'll be finished very soon. Okay, I'm gonna go forward. Okay, interesting. Not enough information, right? So let's look at this equation here. Okay, so if delta G was just defined by delta H, it would be equal to delta H, but that's not what we see, right? We see delta G is equal to delta H minus temperature times the change in entropy, right? So let's break this down. So what is delta G, right? It is Gibbs free energy, work free to do. What did I write here? Energy free to do work. And that defines if something's going to be endergonic or exergonic. It defines if your reaction is going to be spontaneous or non-spontaneous. Delta H is enthalpy. That kind of is a reflection of the chemical potential energy based on like bonds or like just chemical interactions. And this will tell you if something's exothermic or endothermic, right? And then you'll have the temperature here. Never forget to convert to Kelvin just by adding 273 there. And the last part is entropy, right? We can have a positive or a negative entropy here, which can influence. So let's say we do have an exothermic reaction, and this will be negative. But we also have negative entropy, okay? And let's say this negative entropy, this causes the reaction to get so big that this positive charge here overwhelms the rest of the equation, right? It overwhelms this negative delta H. So then the Gibbs free energy, the change in Gibbs free energy will be positive, okay? So we can't tell what's gonna happen just from the delta H. We need every part of the equation. I wrote out all the Ka